Set your alarm for August 11th. So right now the Perseid meteor showers are going on, but you can't see them that good. August 11th, 12th, and 13th, they're gonna peak. What does that mean for you? It means 50 to 100 giant fireballs crossing the sky in under an hour. Every hour throughout the night. So that gives you a lot of opportunity to make wishes. Make sure to follow me. I'm meteorologist Jody Kodish if you like heads up like these.
Is the Large Hadron Collider going to destroy the world in 2022?
An enormous underground tunnel at CERN on the border of France and Switzerland. Magnetic fields 100,000 times stronger than the Earth's. Protons accelerated to 99.999999% of the speed of light to the highest energy ever used in a collider experiment and smashed together, briefly recreating the conditions of the Big Bang. When it turns on again next year, is the Large Hadron Collider going to destroy the world? The answer is very simple. No. How do I know this? Well, first, because I work here. I live on the world, and that wouldn't make any sense. And second, and more importantly, the stars and planets out in space are being bombarded by higher energy particles all the time, and this has been going on for billions of years, and they still exist, including the Earth. When we say we collide protons at the highest energy ever used by humans in a collider experiment, the key phrase is that one there in the middle, by humans. It's true. The Large Hadron Collider is an impressive achievement, a scientific and engineering marvel that allows us to search for new particles like the Higgs boson that could help us answer some of the biggest open questions in physics. And we humans may think we're clever, and we may be very proud of our proton collisions at 13 tera electron volts, but we're no match for nature. For example, a few kilometers above your head right now, protons zooming in from outer space are smacking into the atoms in the upper atmosphere at energies thousands of times or greater than those we use at the Large Hadron Collider. But someone on the internet said that the Large Hadron Collider was going to make a black hole. A black hole? No. The hypothetical object would be a mini black hole, not a cosmic black hole like the supermassive ones in the centers of galaxies. It's literally impossible for us to make one of those at the Large Hadron Collider because we're colliding minuscule protons, not collapsing entire stars. A mini black hole would be a tiny object that would technically satisfy the equations of a black hole if some currently speculative theories are correct. And if we make one in the Large Hadron Collider, it would evaporate immediately. It wouldn't hang around long enough to start accreting matter like a cosmic black hole. And again, if we could make a dangerous black hole at the Large Hadron Collider, then the universe would have made one in our upper atmosphere via cosmic ray collisions many, many times already. This hasn't happened, so it's not going to happen at the Large Hadron Collider. All of these scenarios were studied in great detail before it turned on, and the resounding conclusion over and over is no, the Large Hadron Collider is not going to destroy the Earth. The Earth has existed for 4.5 billion years, and humans have shown up for only the last tiny fraction of that history, and just by building a humble particle physics experiment, we're not going to destroy humanity. To do that, we'd have to do something much more catastrophically foolish, like extract hundreds of billions of tons of fossil fuels and burn them into the atmosphere and allow oil companies and their governmental allies to gaslight us for decades until it's too late and the oceans boil.
In the tropics, there are 2 days a year where the sun will be absolutely directly overhead at noon. It's called Lahaina noon, and it makes things look really weird, like they haven't fully rendered or something. And vertical objects like flagpoles, bollards, and telephone poles get no outward shadow at all. It happens when you're at the closest point on Earth to the sun, called the subsolar point. And the subsolar point travels all the way through the tropics, so if you live between the Tropic of Cancer and the Tropic of Capricorn, you've probably seen it, and I'm jelly. The only US state that gets to experience Lahaina noon is Hawaii, and there's a cool sculpture there called the Sky Gate. During most of the year, it has a curvy and twisty shadow, but during Lahaina noon, it casts a completely circular one. Michael from Vsauce was there. He's how I heard about Lahaina noon. Lahaina means cruel sun in the Hawaiian language. And in ancient Hawaiian, it was, forgive my pronunciation, Kau Kau La I Kalolo, which means the sun rests on the brains. How about one more picture? Just looks a little off, right?
I did not like this metal sculpture, so I cut it up and remelted it in the furnace. I pour molten metal into the orbes to make the sculpture. The metals I use, in addition to the pouring temperature, determine the shape of the resulting sculpture. This one is huge, and I am very pleased with the shape and shine. What do you think?
What have you got?
You're joking. Science!
Oh goodness. Who's gonna tell her? Let me save you some time, bestie. If you click the link in my bio, it'll take you to my TAP link, where you can click on lactation and medication consultation, which will take you to the website of my business that I own. And if you click the drop-down menu, there's an option to contact us, where you can pin your poorly worded email and fill it with all that misguided anger. And then click send, and it'll come straight to me, Dr. Savannah Malm, and then I'll expend exactly 0 energy reading that nonsense and send it straight to the trash.
Glass that makes a bullet shatter? Yes, this is real and it's called a Prince Rupert's drop, but despite its perceived strength, it's actually weaker than Kansas City's run defense if you find its Achilles heel. That weak point is at its tail and makes the entire thing explode. So how on earth is the glass so tough and weak at the same time? Well, part of the mystery relates to this uncooked noodle. This is not your average noodle. It's a whole wheat. Just kidding, it is average, but it's still important. It shows how materials have different strengths depending on if they're being compressed or stretched. It's decently hard to pull the pasta apart with your hands, but it easily snaps under compression. This clip actually shows more bending than compression, but it was too nice of a slow-mo to leave out. Anyway, concrete/cement is the opposite. It can withstand 10 times more force in compression than in tension. That's why it's often used in buildings and bridges to support large compressive weights, but also why engineers have had to learn techniques to improve its tensile strength in order to avoid catastrophic cracking and failure. Glass is just like concrete, but has an even more extreme difference. Glass's compressive strength is 210 times more than its tensile strength. Although notice how that doesn't mean it's stronger than concrete, we're just comparing it to itself. Now this is great and all, but how does it relate to Prince Rupert's drop? Don't worry, we're almost there. Why should you never store liquid gallium in a glass container? Well, as the gallium cools to room temperature, it freezes and expands, pushing liquid up and out of the container. Now that elevated liquid is exposed to the air, so it freezes over and creates an enclosed container with liquid gallium still left on the inside. As that inner gallium freezes, it tries to expand but can't, so instead pressure builds up until the glass breaks and you're left with a mess. Water also expands as it freezes, which is actually super clutch though, because otherwise ice wouldn't float and all the fish would get frozen each winter. But anyway, water and gallium are the weird, unintuitive exceptions, not the rule. Glass, however, is like most liquids in that it shrinks when it becomes a solid. When you first drop the molten glass in water, the outer shell freezes almost immediately, making an enclosed, rigid container. As the inner liquid glass continues to freeze, it still wants to shrink, but now needs to pull the outer rigid shell with it. By the time the entire drop is frozen, the outside of the drop experiences a massive compressive stress, estimated to be between 90 to 170 megapascals or 13,000 to 25,000 psi. The inner glass experiences that force equal and opposite, meaning it's the middle part that's in tension, and the tensile stress is important for the explosion part, but for now let's focus on how that outer compressive stress makes it strong enough to shatter a bullet. The predominant mechanism for failure in brittle materials like glass is brittle fracture, which starts with the formation of a crack. The compressive stress helps keep the glass resilient because it opposes the start and spread of the crack. That means to get a crack into the explosive tension region, you'd need a larger impact than the massive compressive force we already discussed earlier. Small bullets can't do that on the large part of the drop, but a lot of things can do that near the tail, where the skinniness of the glass makes it easier to bend and shear. Once that compressive surface is broken, the overall balance between compressive and tensile forces is broken, and a chain reaction occurs, releasing all the stored energy in a beautiful explosion.
What it would look like if you fell deep into Saturn's atmosphere.
This is a map of the continents of the Earth showing how much ultraviolet light lands in each latitude. It turns out the closer you are to the equator, the more intense the ultraviolet. We use reds and purples. But then as you move away from the equator, we change the colors to orange, yellow, greens, and grays. Now here's the same map of the same continent with just one color. And it turns out that everybody on Earth is descended from people that live here. in Africa. And then as groups of us moved around the world, the color of our skin had to change. And here's why. Our skin is where we make vitamin D. If you don't get enough ultraviolet, you don't get enough vitamin D. But if you get too much ultraviolet, then you break down your folates. You have to have it in perfect balance. And because the ultraviolet varies, the color of our skin varies. And that's it, everybody. That's why we have different colored skin. But we're all one species. But we're not treating each other fairly. Not everybody's getting an even shake. So it's time to change things.